How you doing? I'm Mr. Rose, and today we're going to continue to talk about rotational motion, specifically finding the moment of inertia of a solid disk from University Physics textbook, 13th edition. This is question 959. The question asks us to show or derive the moment of inertia of a uniform disk that's solid using the equation I is the integral of r squared dm, which is our general form for a moment of inertia of a continuous object. So things that I want to know about this. It tells us in the problem that we have uniform mass m and the radius of the disk is r. So we know that we're going to use this mass per unit area relationship. So I can say the mass of my entire disk, or mass per unit area of the disk, is the mass of the disk m divided by pi r squared, which is the area of the disk. So this is my mass per unit area. Notice in my equation, I'm in terms of dm, and I have r, and I know r, or in what's going to eventually be my x direction, or my distance direction, and mass don't play together because I can't integrate about some constant. So we need to make these two things agree with each other. How are we going to do that? What I've done here is I've separated my solid disk into this solid ring. I'm taking a very small piece of that ring that I could call dx, and I know this ring has a uniform mass density, just like my disk has a uniform mass density. So the first thing I want to know is I'm going to consider this ring, and I know the area of my ring is going to be the ring circumference times its width. So the area of that ring is just going to be 2 pi x times dx, however many small dx I have to get that entire area of the ring. I can set that at any point in this disk. Come over here to find the mass of my ring, is the entire mass of my disk multiplied by the area of my ring. So if I multiply the mass of my disk multiplied by the area of the ring, I'm left with the mass of my ring. You can see I have my pi cancels out, so the mass of my ring, or any ring at some distance x, is just 2 times the mass of my disk, 2m divided by r squared. So now the moment of inertia for any one single ring. Now this is where we're getting a little bit confused in class. The moment of inertia for any one single ring is just mr squared. So I know the mass of my ring, 2mr squared times x times dx, that small x value, times now my r squared value, my r value, which is r squared in the formula. My r value is just whatever distance I am away from the center of, my rotational axis about the center. So whatever my x distance is, that becomes x. Multiply through my moment of inertia of any single ring at some distance x away from the center is just the total mass times x squared, or 2m r squared x cubed times some part of my ring, dx. Now what we're doing to utilize this formula is what we've done inherently, is we have taken my relationship of r dm, and I've already incorporated that here. Actually, I've already incorporated that here. This is my mass dependent on some distance or some portion of the ring x. So now I'm going to take not just one moment of inertia, but all of the moments. A ring, a ring, adding all those rings up to be the moment of inertia for my disk. So I come over here, I know the moment of my inertia of my disk is the sum, or the antiderivative or integral, of all of my rings. That's all of my rings times some dx, some distance dx. Again, it's kind of a trick. I've already incorporated my distance x in terms of mass. That's how we did it, knowing that I had a mass and area relationship. So I have the integral of 2m r squared x to the third dx. My x and my dx are now in agreement in my formula. This is for the disk, or the inertia of all of my rings. I can take out all of my constants. 2m r squared, that's a constant. Mass is a constant, r is a constant. 2m r squared times the antiderivative of x cubed from 0 to r. From the origin to radius r. The antiderivative of x cubed is x to the fourth over 4. All of that is a constant. At 0, that's 0. All of that zeroes out. At r, don't know where to go here. At r, I have 2m r squared times r to the fourth over 4. My r squared cancels with this to get r squared. That cancels, gets me a 2, and I'm left with 1/2 mr squared. This is how we can utilize an antiderivative even if I have no agreement here, utilizing a mass per unit area relationship, finding the mass of my ring per unit distance, and then finding a moment of inertia of one thing. I know the moment of inertia of all of my rings, adding them all up is just integration. Subbing that into my integral, solving my integral. Hopefully this helps. That's all I have for you today. Please feel free to like, comment, subscribe, and I will see you next time.